the IDEAS Productivity Project. The project is funded by the Exascale Computing Project in collaboration with the U.S. Department of Energy, Computing Facilities at Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez. Ashley Bark and I will be the hosts for today's webinar, Tools and Techniques for Floating Point Analysis, and the webinar will be presented by Ignacio Laguna. He works at the Lawrence Livermore National Laboratory at the Center for Applied Scientific Computing. Ignacio's main area of research is high-performance computing, and he also works on including program models and systems. He's a 2019 Better Scientific Software Fellow. You can see the call-out in this slide. And he helps code teams to improve the reliability of scientific software through analyzing and debugging floating point software. So going back to the fellowship program, it gives recognition and funding to leaders and advocates of high-quality scientific software. So if you go to that link, https://BSSWIO fellowship, you have more information about the program, and also applications for 2020 are now open. We have, in quotes, sold more than 180 tickets for this webinar. All attendees have been muted. As Ashley mentioned before, we'll be receiving questions through the WebEx chat, but we prefer that you enter your questions in the Google Doc. You can see the link to that doc. The webinar will have breaks, so the speaker can, Ignacio can respond to the questions that come in. With that, Ignacio, please.
All right, I'm going to share my screen. Can you see my screen now?
Yes.
Okay, perfect. All right, well, thank you very much for the introduction, Osni, and also thank you for inviting me to give this webinar. So one of the things that I do at LNL is to develop debugging and correctness tools, and also performance analysis tools for HPC applications. And one of the areas in HPC that really intrigued me is floating point. As we know, floating point is used everywhere in scientific computing, but even so, I still find it difficult. One of the reasons is that understanding all the details of floating point arithmetic is hard. And another problem is that there are not many tools. I find that there are not many tools to analyze floating point. There are several tools to analyze the performance of HPC applications, but not necessarily many tools to analyze floating point. And the few tools that exist are developed by computer scientists, mostly computer scientists like me or others, and but they are not necessarily well known in the broader community of computational scientists. And so the idea of this webinar is to advertise a bit more some of these interesting tools and areas of floating point analysis in HPC. So this webinar will cover specifically three things. The first is some interesting areas of floating point analysis in HPC. The second is some potential issues that may arise when writing floating point programs. I will show you real examples of issues. When I say issues, I don't necessarily mean bugs or software defects. What I mean is potential problems that you may encounter on which you need to pay, or you should pay, careful attention. And the third is some tools and techniques that you can use to mitigate or sometimes to get more insight from some of these issues. And when I say tools, I mean software that you can download and install and run today, as opposed to research papers that don't necessarily have an existing tool. One disclaimer is that this webinar doesn't cover all aspects of floating point analysis. We cannot do this in 1 hour. I will focus particularly on high-performance computing applications. I don't mention, for example, issues on finance applications or game applications, for example. And also keep in mind that this is my view of the issues and tools that I see as a researcher in a national lab. I don't mean this to be a comprehensive overview of all topics and tools that exist in the domain of floating point. So just keep that in mind. So I want to start by giving you an example of what it takes to debug a floating point issue in a real code. So this is an example of a floating point problem that occurred last year in the development of a new mini application. This was a new hydrodynamics mini application developed here at LNL. And so this happened in the early efforts to port this code to a new system. In this case, this was an IBM machine with Power 8 processors and NVIDIA GPUs. And as you probably know, moving to a new system, this means using new compilers and different, sometimes using different compilation flags. And for a particular case, the energy value, so this application calculates an energy value, and there was a significant difference when we use the XLC compiler. XLC is the IBM compiler for C. And in particular, when we use -03, so high optimization level. The other compilers in the system produce the expected result, but not XLC. And as you can see here to the right of the slide, and the question we had was, well, we had several questions. One of them was, what part of the program is making the compiler produce this very different code? Keep in mind that programmers really want to use O3 or higher level of optimizations to get all the possible performance from a machine. So really using lower levels like O2 or O1 are not really a good option. And this problem took several weeks of effort of expert debuggers to diagnose. We isolated the problem to a single function in a region of code that was actually producing subnormal numbers, and this combined with -03, which can significantly change the semantics of the program, produce incorrect results. So this gives you an idea of why having effective tools and techniques to debug these problems is important, and we will come back to this case later in the presentation. There is a standard that defines floating point arithmetic. The latest version of the standard was released in 2008. I will be talking about floating point arithmetic in the rest of the presentation, so it is useful to quickly go over the key concepts of the standard. One of the concepts is a format, so it defines how to represent floating point data. Special numbers, such as infinity, not a number, subnormal numbers. Also rounding rules, rules to be satisfied during rounding operations. Some arithmetic operations such as trigonometric functions and the behavior of them. And the standard also defines exception handling. For example, what happens when you have a division by 0, or you have an overflow or an underflow, and things like that. One of the important problems in developing reliable floating point software is that programmers sometimes don't fully understand all the details of the standard. There is a recent paper titled, Do Programmers Understand IEEE Floating Point? And I'm giving a reference here for this paper. So the paper presents the results of a survey taken by 199 developers. And the survey questions about key aspects of the standard. For example, aspects related to optimizations, the use of fuse, multiply, add operation versus flush to 0. And for example, things like, can fast math result in non-standard compliant behavior? And what the study found is that developers do little better than chance when they are tested about core properties of floating point, and yet they are confident. So I'm giving here a reference to the paper, so it's a good read. I would recommend to read this paper. One of the situations that we see sometimes is that when programmers see an incorrect numerical result, they say, well, you know, it's just floating point error or rounding error, so don't worry. The reality is that there are many factors that are involved in producing an unexpected numerical answer. I list some of them here. So one of those is the precision that you're using, right? Are you using double, single, or half precision? The compiler that you're using a proprietary compiler or an open source compiler? We have found that the proprietary compilers tend to be more aggressive in the optimizations and then tend to give significantly different results compared to the open source compilers. The language semantics is also important. So, for example, floating point is underspecified in languages like C. So the semantics for C are not necessarily the semantics for other languages that you may be using, like Python, Julia, or something else. The optimizations level is also very important. You should be careful with -03. I'll show you later an example of some examples why 03 is dangerous. Just pay attention to that. The architecture is also important. Are you running this on a CPU host or on a GPU or another accelerator? So those are things that you need to keep in mind when you see a result, numerical result that you don't necessarily expect. Now, there's this question we have, which is how do we know what floating point code can produce variability? Or in other words, how do we know what kind of code we should be careful about when we're running the code in GPUs or in a CPU or with different compilers, right? So we're developing a tool called Variety that allows that hopefully will help us answer this question. So what this tool does is that it allows us to identify programs that produce floating point variations. So the idea of the tool is that it generates random tests and then compiles the test with different compilers in a given system, and then it runs the test with a given input and checks if the results are different. So I'm going to show you a few examples of some floating point tests that we found with this tool on which we saw large variations. So here's an example of a random test. It's a random kernel that this tool found. You don't really have to understand the test here. What you have to see is that this is a function that was randomly generated, and we compute a variable comp or a computation comp, and then we print the value of that at the end of the kernel using 17 digits. And so in this particular case, so the tool tries several random tests and several inputs. And so for a given input, when we run this in IBM system with Power 9 cores and NVIDIA GPUs V100, this is in LNL Lassen system, and we use optimization level of 3 for CLAN. Running this on the host, we get a NaN, not a number value. But when we run this in the GPU with -03 using NVCC, we get a total different result. So as you can see, the GPU result is actually a normal number, whereas the result from the host execution is a result of an exception, right? So it's not a number value. Now, here we're using 03, right? So we're using high optimization level. And we know that when we use high optimization levels, the compilers can optimize the code and can produce code that could eventually result in a very different value. So maybe because we're using 03, this is sort of expected. I wouldn't expect a difference of this size, because it's really a number versus a non-number. But let's say 03, allows this kind of behavior. Now the question is, what about when we do 00, right? When we tell the compiler, typically when we do 00, we're telling the compiler, I don't want any optimizations, right? I want you to compile the code. I want you to generate code as close as possible to the program that I wrote. And so the question is, can with 00 still see these cases? And actually, we found cases like that. We're finding cases like that. So there's another random test that we found where for this input, this is running all in the host architecture, not the GPU, just the host architecture. When we run this with Clang and GCC and Excel, we get different results from Excel, as you can see here to the right. Again, this is not optimized code. This is pure O0, right? No, we don't tell the compiler to optimize anything. Now, the difference here is that it's actually a fuse multiply add. So this particular system we're running on supports FMAs operations, and for some compilers, FMAs are not considered a significant optimization, and this is the case for the XLC compiler. So when we do XLC, and even when we're doing O0, this compiler tries to generate FMA operations whenever it can, versus Clan and GCC doesn't do it, because they are thinking that, well, when we say O0, we mean we don't want to do FMA. And that's the main reason we have this result. So to really have the three numbers, to have the same numbers in the three compilers, we need to tell XLC that we want O0 and that we don't want FMA. So that's another thing to keep in mind. Another issue is that even when we have a standard for floating point, some architectures do not implement the standard fully, and they have what they call deviations of the standard. So one example is NVIDIA GPUs. In NVIDIA GPUs, there are no mechanisms to detect exceptions, and exceptions such as division by 0 or underflows are always masked. And so what this means is that there may be programs that may have numerical incorrect results because of an exception, and the programmer doesn't know about it because there's no mechanism in the GPU to detect that, right? And so this may be a little bit scary, but fortunately, we are developing tools to solve this problem, and I'll show you later a tool that we are developing to detect these problems in GPUs. So in the rest of the webinar, I will present some existing tools and techniques for three areas of floating point analysis: exceptions in GPUs, compiler variability, and mixed precision tuning. Unfortunately, as I said before, I cannot cover all the areas or problems related to floating point, but these are three areas that I believe are important today in scientific computing and HPC. At this point in the presentation, I could take maybe one or two questions.
Hi, Ignacio. Actually, we have three.
Okay.
So the first one, anything interesting in IEEE 754 update from 2018?
So FMA is one of the most interesting things, I would say. So the standard started allowing FMA operations, which are now supported by some hardware, like GPUs, for example, support that, but not all hardware support that.
Okay, next. Is floating point ever reproducible? Are there reproducible libraries that perform floating point?
It depends on what level of reproducibility and what kind of reproducibility you are thinking about. I would say it's very difficult. We find a lot of problems when trying to reproduce a floating point between machines. As I just presented, there are issues with compilers, depending on, even in the same architecture, even when you're telling the compiler, do not optimize the code, compilers produce different code. So it's very, very difficult to reproduce it.
Okay, so next, what is in quotes, random test? I think that's because you used random test for
Right, so the random test is a program.
Okay, so it continues. How are these generated? The examples shown all seem like they are examples that use FMA.
So we have a grammar that defines what programs can be generated. This grammar is a subset of the C language. The grammar supports features that you would see in HPC applications like for loops, if conditions, arithmetic operations, math calls, and things like that. And basically, the algorithm uses the grammar to generate random programs. So it generates lines of code using this grammar. It can generate simple tests, or it can generate very complex tests. Not all the cases that we have produce FMA. Probably the one that I presented just as the case, but not all the time.
One more question, Ignacio.
Mm-hmm.
So is the IBM, when you use the IBM compiler with the -0,
Mm-hmm.
is that result used in FMEA the correct one?
You know, to say what is correct here is difficult because the random test generator doesn't necessarily indicate what is the correct answer. All we can do here is to generate random tests in a given system and use all the compilers in the system to see what compilers produce, what group of compilers produce the most reproducible results. So essentially, what we want to tell to the users is, okay, so you have this system with 5 or 6 compilers. What compilers should you use when you're running a code on the GPU versus running code on the host? And reproducibility is important for you, which compilers you could use. Whether the answers are correct or not, we cannot tell that.
Okay, so that's it. Please go on.
Okay. So in the rest of the webinar, I will present some existing tools and techniques for 3 areas. Well, I just mentioned that, I guess, that we're going to be presenting analysis and tools for these 3 areas. And the other thing I want to mention is that all the tools that I present are available here in this website, fpanalysistools.org. This is a website that we maintain for a tutorial that we give, but you could also find links to the tools that I present here, and some other tools as well. Okay, so moving to exceptions in GPUs. So if we look at the problem of trapping exceptions in floating point exceptions in CPU code, that's a solved problem. So when we have a CPU exception, this is usually signal, or it can be signal. So the system can set a flag, or it could take a trap. You could get a register set as well. So for example, in a Linux system, can also cause the floating point exception signal to be triggered by the system, and then you can catch these using a signal handler, for example. So it's not a problem for CPUs. Problem is with GPUs that they don't support these, and as of right now, there's no mechanism to detect these exceptions. And as I mentioned before, so you may have hidden exceptions in your CUDA program if you don't do some checks, right? In the code, you may see these exceptions, or they may occur, but you don't know that they are occurring. You could use some of the API calls from the CUDA specification to, for example, you could actually add printf statements to your program, as many as possible, and you could be printing the results of many of your floating point operations. That's one approach you could use. Another one is you could have a programming checks. In CUDA, for example, there is these functions isNaN that you could use to check if a floating point is a NaN, or you could have also, they also have support for isInf for infinity. As you can imagine, these solutions are not ideal because you have to write this in the code, but most importantly, this requires significant programming effort. The other problem with the CUDA checks is that they don't support all classes of numbers. So for example, there's no check for if you have a subnormal number, right? So you'll have to build that by yourself. So we want a more automatic way to detect these errors in GPUs, and for this reason, we're building this tool, FPChecker, that allows us to automatically detect the location of floating point exceptions in NVIDIA GPUs, and we have been running this tool in the LNL systems, LAS and Sierra, to help users to detect these problems. The tool reports the input operands. It uses a software-based approach using the LVM compiler. So the design is all based on the LVM compiler. LVM is one of the solutions for the systems that we have in the lab. It's an open source compiler, so we can develop extensions to the compiler to check for these problems. And so essentially, the design is that the compiler splits the compilation process into the host code compilation and the device code compilation. And in the device code compilation, we instrument the code and add a runtime that will check whether or not you have an exception in a floating point instruction for all of the threads in the GPU. And the usage is pretty simple. You have to compile your CUDA program with Clank. That may be a problem for some codes. So basically, you need to make sure that instead of using MVCC, you're going to compile with Clank. Clank supports compilation in CUDA. It doesn't have all the features that MVCC has, but it has a very good functionality, I would say, that would allow you to compile many programs. And then you have to add some flags to tell the tool to load the instrumentation library and to include a runtime header file. That's pretty much all you have to do. We also check for what we call Leighton underflows or overflows. So these are essentially numbers that are not, they are not yet infinity or subnormal numbers, but they are kind of like in the limit, in the border of the normal numbers. So we do check for that as well. So you can see, for example, you have a computation that is getting really big or really small, and you need to pay attention to that. And if you see an error, you see a report like this where you can see the error, the operation, the input, the file, and the line of code that caused the error. The slowdown that we have seen so far by testing this with about 3 to 4 applications is in the order of 1.2 to 1.5x. All right, now we will talk about compiler-induced variability, but before I move there, I could also get questions if we have.
Yes, there is one here. It's perhaps related to one of the previous questions. It's maybe a useful metric to be able to provide from these tools is to give users an expected absolute or relative tolerance to expect in floating point values across the range of compilers, flags, etc., that are available in a given system. For common cases, not exceptional ones that result in unexpectedly very large diffs. This is more, I think, a kind of a suggestion than a question.
Okay. Okay. Yeah, that's a very interesting suggestion. Yeah. Thank you very much.
And there's someone typing right now. Okay, so is it possible that FP checker changes answers? Sometimes a bug only shows up in a release build and not a debug build. Could something similar happen with FP checker?
For this kind of tool, I don't believe that this will be the case because this will not alter the schedule. I would say that you would see, because we do check. So basically, what happens is that every thread in the kernel that is running the GPU will perform exactly the same operation. We don't synchronize between threads. We don't perform any synchronization between threads. So every thread will go and perform the same check for each floating point instruction. There will be some overhead, yes, but there's no synchronization. And if one of the threads sees an exception, then we have an atomic operation where every other threads will basically go away, and this thread that found the problem will print the report and will abort the kernel. I don't see that this could change the results or the computations that are performed, because these are, side-by-side operations that we do as the program runs. Yeah.
Okay, so let's see. I think. Okay, so are formalized tools feasible on large-scale codes, e.g., Coq plus FlockQC?
Sorry, I didn't get it. Can you say that again?
Are formalized tools feasible on larger scale codes?
Formalized. You mean formal methods tools? I don't know what is formal. What is a formalized tool?
Maybe formal. So I read formalized, but perhaps the participant meant formal.
Formal methods, maybe. Formal methods tools like model checking, verification. So I think they're feasible, but we need to do more research into integration. We actually have a workshop on correctness in HPC in supercomputing. Actually, I'll mention this workshop at the end of the presentation, where we are basically getting together, researchers in the area of correctness, formal methods, verification. We're getting together into this workshop to help in the process of making these tools more available, making these tools more usable in production codes. I haven't seen any of these tools to be used in a large production code personally, but I think it's possible. I think it's feasible with a little bit more research and work.
Okay, please continue.
All right. Thank you for the questions. Very, very nice questions. Thank you. Okay, so let's move to compiler variability. So I will talk about some of the techniques that we use to debug this mini application case that I presented in the beginning of the webinar. We use a technique called delta debugging, which helps us to manually identify the origin of the problem. And also I will present a tool called Fleet that performs this analysis in a more automatic manner. Okay, so I want to bring back this case again. The question here is, how do we debug this? Right, so how do we find where the problem is here? So the root cause analysis process that we follow to debug this problem was that given a buggy program, first we want to identify the file or files that are involved in this issue. Then within this file, we want to identify the function that could be causing the problem, and within this function, the lines of codes that are possibly involved in the problem. So to analyze this problem, we use an algorithm called delta debugging, which is widely used in debugging. It is used in debugging compilers, in many other software code bases. In particular, we use delta debugging to identify the file and function that causes problem. So this algorithm identifies inputs that make the problem manifest. Essentially, it identifies the minimum inputs. So if you eliminate one element from this input, the problem doesn't manifest itself. And there's an algorithm for this, but I will not show the algorithm because I think that's boring. I think it's more interesting to look at an example. So I'm going to show you an example of how this actually works for this particular kind of debugging. So let's look at this example. Let's say we have a program that has 8 functions. This is our input. And let's say we get wrong results when function 3 and function 7 are compiled with high optimization, but the remaining functions are compiled with low optimization. Now, we don't know that function 3 and 7 are the problem, right? Because we compile the entire program with high optimization, but the algorithm will find that 3 and 7 are the culprit. And so what the algorithm does is that in step 1, it splits the input, in this case the functions, into 2 chunks. And then in step 2, it compiles chunk 1 with low optimization, and then chunk 2 with high optimization. It does the same for chunk 1 and 2, but in this case, chunk 1 with high optimization and the other one with low optimization. Now, in these 2 cases, the error does not manifest because, as we said, the bug is caused when function 3 and 7, both of them are compiled with high optimization. But in these 2 cases, we did not compile both of them with high optimization, so we don't see the problem. So the algorithm doesn't find anything interesting here, right? So now what the algorithm does is that it uses finer chunks or smaller chunks. So instead of 2, now we have 4, right, as you can see here. And then it compiles chunk 1 with low optimization and the other one with high optimization. And in this case, we see the problem. We see that we have an incorrect answer. And this is the case because 3 and 7 are in this chunk where we use high optimization. So now we can essentially safely remove, we can remove chunk 1 from the search, and then we continue with the second chunk. We continue doing the same thing, the same algorithm. And at the end, the algorithm tells us that 3 and 7 are the ones that cause the problem, because when you compile only those two with high optimization, you see this error. So we implemented a program that runs this and uses the Excel compiler to change the optimization levels, and we were able to debug this problem and to identify essentially a particular file in the application and a function that was causing this problem. And so here you can see the result. So when we do O2, we get a correct energy value. When we do O3, everywhere we get the incorrect value. But when we do O3, everywhere except that function that we found, we get a value that is more similar to O2. Right? So you can see that the problem is now going away. So we also found other problems in this code. One of them is the use of subnormal numbers. We found that the combination of subnormal numbers and high optimization levels is a dangerous combination. So my suggestion to all programmers is to not use subnormal numbers at all. And I have two reasons. One is that it may impact the performance, because we know that often in many architectures, including GPUs, subnormal operations are slower, tend to be slower. There are details about that. It also depends on whether you can do FMA or not in the operation, but they tend to be slower than operations that don't have subnormal numbers. And the other reason, which I think, in my opinion, is more important, is that you lose too much precision when you are computing in the subnormal numbers domain. And so here's an example of how inaccurate subnormal numbers can be. Here we multiply a constant by, so the constant here is a subnormal number. So we multiply that constant by 1 divided by 3. Right? So we have 1 divided by 3, which is the original value. We multiply by this constant. This constant is a subnormal number. We print the result. And then we denormalize it. We divide it now by the constant, right? So we are restoring the value back. But as you can see, we don't get the initial value, right? So we don't get the value that we get when we divide 1 by 3. And this can be solved if you use higher precision. Instead of using double, if you use long double, you don't have this issue, right? You restore the original value, essentially, even though you are multiplying by a denormalized value. Right? So the takeaway here is that you should not be operating in the domain of subnormal numbers. Often we see applications doing it. Sometimes they don't care. Sometimes they think that the application can handle it. They say, they tell us, well, you know, my algorithm can handle subnormal numbers, so I don't have a problem with that. But sometimes they don't know. Sometimes they don't know that this is happening, which is scary to me. So the question is, can we actually avoid subnormal numbers? By the way, we can have a full webinar only on this topic, on the topic of how to have applications avoid subnormal numbers. So here I'm just going to give you some ideas to avoid subnormal numbers. So one is you could use higher precision. As I presented in the previous example, if you use higher precision, that is not a problem necessarily. It could be a problem, but maybe not for the inputs that you have. Now, this is a research problem because now you want to do what's called mixed precision, where possibly you're doing double precision everywhere, but in some parts of your program you're doing higher precision. There are questions about how to use the casting operations, because you have to convert those results to a higher precision. So this is really a research problem that is going on these days. How do you do that effectively without impacting the performance of your code? And later in the presentation, I'm going to present some examples of why mixed precision is hard. You could do scale up, scale down, right? So if you scale up the computations you have, you're not close to the domain of subnormal numbers, but then you have other problems, right? Because most of the precision that you have is in lower numbers. So if you scale up, you also lose precision. It could work for simple problems only. I don't know. I mean, I haven't tried this in large applications. So it may solve the problem, but it may introduce other problems. So something to keep in mind. You could also flush overflows to zero. So some architectures allow you to do that. GPUs is one of them. What this allows you is that whenever there is a subnormal operation, it will be promoted to a zero value. This doesn't fix the underlying problem because your algorithm is still generating subnormal numbers, right? But it eliminates performance issues because now you will not have operations in this domain. These values will be converted to zero. And there are algorithmic changes that you can do, and there are many papers that talk about different algorithms that you could use to avoid subnormal numbers. There are actually a few books that talk about this. So it's a topic for an entire webinar. I won't go into the details of this. I just wanted to mention these possibilities. So in the previous example, we identified the root problem in a single function using delta debugging, as I mentioned. This process was very manual in essence. There's a tool that you can use to isolate problems like this in a more automatic manner. The name of the tool is FLIT. FLIT provides a method to analyze compiler-induced variability. This tool provides multiple levels of analysis. It can determine compilation options that influence floating point variability in programs. It can analyze the trade-off of reproducibility and performance for a given compiler. It can also identify files, functions that cause variability due to compilations, like the example we saw before. It uses a bisection search algorithm as opposed to a delta debugging algorithm that we use. And this can identify the function that caused the problem that I mentioned before. The main developer is Mike Bentley at the University of Utah. And again, if you go to this link that you see in the bottom of the presentation, you can find a link to this tool. So now we are moving into the area of mixed precision, which is the last part of the presentation, but I can take questions here as well.
Okay, so there are, I think, three questions here for. First, are subnormal numbers same as underflow?
If you go to Wikipedia, it says yes, they are the same. I forget what the standard says about that. I personally treat them as underflows.
Okay, the next question then. Khan, emeritus professor at UC Berkeley and the father of IEEE 754, has several examples of where subnormal numbers help improve the results of expressions.
Mm-hmm.
Do you have comments on that?
That's an interesting point. I haven't seen cases like that. Here in Livermore, usually we see problems between subnormals and when they are combined with high optimization levels. Mm-hmm. They produce very, very different results, like the example I presented with the Excel compiler. Personally, I haven't seen any case where subnormal numbers improve the results. That's an interesting point.
So next question then, Ignacio. In the fixed, in quotes, Raja example, the value still seemed to differ in the fourth significant digit. Isn't that still really bad?
Yes, that's correct. So actually, in this case, we had to go deeper into the problem. We identified the function, right? And so when we compile this function with lower optimization level, we improve the result. But actually, maybe I can show the slide here quickly. Here. Yeah, so the result is still not the same, the one that you would expect, the one that we get with O2 or from other compilers. But there are other problems in the code. There are subnormal numbers. And in this function, there are some operations as well that we had to identify. There were some divisions that the compiler was promoting to reciprocal operations. And all of this combined with subnormal numbers produce this error. So we didn't end the debugging at this point. I'm just showing you the process we follow to find the function. But after the function, we have to find the line of code. And when we found those, we actually correct the problem to the expected result. I just didn't show this here in the presentation because of time.
Okay, we have three interesting questions here, but let's please continue, Ignacio. Leave them for the end.
Okay, sure. All right, so this is the last part of the presentation. So this is another area of interest in floating point analysis in mixed precision. The idea is to use lower precision sometimes, or sometimes higher precision, right? In the case of lower precision is to use it in some part of the program to increase the performance of the program. In the two areas that I discussed before, GPU exceptions and compiler variability, we needed to think about correctness of floating point. In this kind of analysis, mixed precision, you have to think about correctness and performance. So the two things, which is tricky. So what you see here is a visualization of LULESH. LULESH is a proxy application that simulates a shock hydro problem. It's developed here at the LNL. And here you're looking at two visualizations of two runs of LULESH. If you look at the visualizations only, you probably won't see any difference. But if you look at the result, the numerical results, you will see a difference. And the difference is that in the first run, we're doing a run with full double precision, so all the variables are in double precision. In the second run, we are using a mixed precision case where some of the operations are in double precision and some of the other operations, are in single precision. And if we let the accuracy to have 6 digits, so in this case, this is accuracy of the second run versus the run 1, which is the baseline because everything is in double. If we let this accuracy to have 6 digits, we can get a 10% improvement of speed up. And if we let the accuracy to have 3 digits of accuracy, in this case, we can have up to 46%. So the question for this kind of analysis is how can we take advantage of floating point mixed precision, right? So what you see here is essentially you're looking at the performance ratio of different NVIDIA GPUs. So the floating point precision levels in NVIDIA GPUs have increased over the years. So in the beginning, the first NVIDIA GPUs only supported one level, only single precision. Then in about compute capability 1.3, they started supporting 2 levels. They could do a double precision and single precision. But the ratio of double to single was relatively low. So you could do 1 operation in double versus 8 operations in single. Right. Later on, we saw architectures that had even lower ratio. But these days, these GPUs support 3 levels of precision. So you could do double, single, and half precision, right? And the ratio is actually higher because you could do 1 in double versus 2 in single. And I think that in the future, we may have a 4th level because right now here the market is dominated by machine learning, deep learning, and we know there are papers showing that you could do training of neural networks with precision lower than half precision. So I'm thinking we may have a 4th level in the future. Now the question is, how can we take advantage of this trend to improve the performance of codes, right? Now mixed precision programming is challenging. Programs have many variables, and if we consider 2 levels of precisions, we have 2 to the power of n combinations. If we consider 3 levels, we have 3 to the power of n combinations. So that's a very large space. So we really need automatic methods to find good configurations for mixed precision, floating point mixed precision. So here's an example that shows how difficult this is. This is a small kernel of an M-body simulation. This is a CUDA kernel. Here, this kernel is computing the forces of the bodies. And so here let's do a little exercise here where we change the precision of some of the variables in the kernel. So initially, everything is double, and we're going to change some of them to float. And we're going to calculate an error to see how well we're doing. In this particular case, the error we're using is the difference of the positions of the particles. You could do different error functions for your application. For this case, we're using this one because it works very well. So when we change all the variables to float, we get this error 15, and we have a speed up of 53%. Maybe it is a good speed up, but I think this error may be too large. Maybe it's too large. So let's, instead of changing all the variables, we're going to change one variable here. When we change one variable to float, we get a smaller error here, but the speed up is 5%, so maybe this is too low speed up, right? Now we change another variable, and the error is very low. It's 1.93, but the speed up is negative. So what this means is now we're making the program slower, so we definitely don't want this case, right? And at the end, we found that three variables, when we change these three variables, we get the smallest error, and we have a reasonable speed up of 11%. So this shows why correctness is not the only thing to consider. We also have to consider the performance aspects of mixed precision. There's a lot of research going on in this domain. I just wanted to mention some of the recent research results on this area. So we have done some work on floating point mixed precision tuning for GPUs recently. We presented a technique called GPU mixer. It's a method that automatically allows programmers to find mixed precision configurations when we observe improvements when the code is executed in NVIDIA GPUs, and where we also maintain the level of accuracy within the constraints that the programmer has. And this paper was presented in the ISC conference a few months ago. One of the existing tools for automatic floating point mixed precision tuning is Presimonius. This tool takes as input a program, an error threshold, and a set of inputs for the program. It performs a search over the types of variables in the program to determine how much precision they need. The analysis produces a listing of floating point variables and also the suggested types, which the tool refers as a type configuration. And when the type configuration is applied to the original program, the final program produces a result within the given error threshold, and it is faster than the original program. The source code for this tool is available. The main developer is Cindy Rubio Gonzalez at UC Davis. Another tool for mixed precision tuning is Adapt. The tool uses algorithmic differentiation for error analysis. This tool allows programmers to understand how the output changes with respect to the errors in the variables of a program. And in this case, it considers a program as a function of inputs and intermediate variables that compute some output. And in the error prediction model, they use essentially a first-order Taylor series approximation around the input to compute what they call error estimates. And so here, for example, let's say X is any input or intermediate variable in the program, and Y is the output variable. Then the error is Y. Well, in this case, the error in Y is F prime of A times the error in X. So the key idea here is to use algorithmic differentiation to obtain F prime of A. This tool provides output sections of the program that need to be in higher precision. So you can see here the left part of the slide to see highlights of a program. And they have used these in several benchmarks, and they have found good speedups. If you want more information of this tool, the main developer is Harshita Menon. He's here at Livermore National Laboratory. You can contact her. All right, so before I finish this webinar, I wanted to mention that we have a tutorial at SC, the SC conference, that covers these tools and other tools for floating point analysis. In the tutorial, we present some of the tools that I present today, but also some other tools I did not present. So for example, tools for controlling non-determinism in MPI programs that could change the floating point behavior of your program. So for example, when you are getting messages in different orders in MPI, and depending on the order of the messages, you compute different, your program computes different floating point values. So you can control this with a tool called REMPI that we present in this tutorial. This allows you to do, for example, a record and replay for debugging. We present other tools as well, for example, for data race checking and so on. This is a hands-on tutorial, so we provide real exercises of how to run these tools in real programs. So if you want to learn more, please attend the tutorial at SC. We also organize a workshop on correctness for HPC applications. And one of the key topics of the workshop is correctness of floating point. In fact, we have a session with, so this year we have a session with 2 papers on the topic of mixed precision. And I have put here the URL of the workshop so you can check the program. So the tutorial is on Sunday and the workshop is on Monday, so there's no overlap, so you can attend the 2 of them. And so here is just a list of some useful references. The first is a group of sites, papers, and videos on general guidance about floating point issues. And the second is information about NVIDIA GPUs and floating point arithmetic. So in summary, there are many factors that can affect floating point results. Keep in mind that it's not only the rounding error. There are aspects such as the compiler you're using, the hardware you're running the code on, the optimizations you're using, the precision you're using, and the parallelism that you're using. Be aware of how compiler optimizations could change the results of the program. Avoid the use of subnormal numbers if possible. You lose too much precision in most of the cases. Pay attention to floating point computations on GPUs. Just because in some GPUs, floating point is not fully implemented, there are deviations and there could be exceptions, for example, that you need to check. And mixed precision involves correctness, but also performance analysis. And finally, probably the most interesting takeaway I want to give here is that the tools community is your friend. We want to hear from you. If you have an issue and we don't have a tool that solves your problem, we would like to develop this tool and work with you to help you be more productive. Thank you to the BSS organization and ECP for providing funding for this work. And here I'm giving you my contact information. Please contact me if you have any questions. And this is a disclaimer that I have to present. But with this, this is the end of my presentation, and I can take questions. Hello, are you still there?
Yes, I believe we have some more questions that have come in. Osmond, do you want to ask them, and I'll hand you presenter?
Yes. So we have some more questions here, Ignacio.
Mm-hmm.
Do you have thoughts, comments on how lossy compression of floating point data and/or using half precision, either at IEEE or homegrown, impacted these issues?
That's an interesting question. There are researchers in Lawrence Livermore that are looking at that. I personally have not dealt with this in real applications. I mean, most of the work that I do applies to large-scale applications that are running in our system. I personally haven't seen this kind of computation where compression is used, but I think it's an interesting topic, very interesting idea to explore.
Another one, do the tools you presented support parallel programs, either OpenMP and/or MPI?
That's a good question. So the tools that I presented here, let's see. So FP Checker is for CUDA, right? We are working on supporting OpenMP as a way to support more, different programming models, because usually we don't have a lot of programs written directly in CUDA, but we do have intermediate layers like Raja that can convert the loops to OpenMP or some other model. So we're working on supporting other programming models. In the tutorial, we do have tools that support OpenMP and MPI. So for example, we have REMP, a tool that allows you to control the non-determinism in MPI. For MPI, it's not very difficult to add support for these tools, I would say, because usually what you have to do is just allow the tool to run in MPI processes in parallel. The problem is, how do you gather the traces in a central point, right? So you could allow the tools to write files for each process and do an offline analysis, or there are other methods we sometimes use, for example, to gather all the traces at the end of the program before or at the point where the program uses or calls MPI finalize. We can gather all the traces and perform the analysis. So MPI is not very difficult, I would say. Multi-thread models are more difficult to add.
Just a comment here before going to the next question. We are going to ask Ignacio to go through all these questions and answer in the Google Doc later, and we'll make the link available to all participants. So another question in us: what is needed for these tools to work with posits and unums? Remember that?
Yeah, that's a good question. You know, I'm going to be honest with you. I think these unums are very, very interesting, fascinating topic. I don't have a lot of experience with unum just because I don't see a lot of programs using this format here in the lab where I perform my work. Mostly I see programs using floating point and hardware implementing floating point. So these are the tools that we are developing. Having said that, I think alternative formats could solve some of the problems of floating point, and perhaps we don't need all these tools, right? If we're using a different format that doesn't have many corner cases like floating point, maybe my job is not needed anymore, and we don't have to write tools for that. But I cannot give more comments on that because I don't really have a lot of experience on unum, and I don't use it regularly. I don't see applications running this regularly. Yeah.
Good. Right. So, do you believe the return on investment in this mixed precision strategy, like much higher code complexity, more difficulty in reproducing, etc., is likely to produce higher performance benefits than other or typical performance improvement strategies?
Well, here we need to define what is other, right? If you want me to compare floating point mixed precision to loop optimizations, aggressive loop optimizations, or something else, we'll have to look into the details here. So all I can say is that the traditional speedup you would expect from something like a floating point mixed precision is 2x, because most codes are doing double everywhere. And if the best you could do is do single. If you lower down everything, you would have something like 2x of speedup. But I think you could do better than 2x if you consider lower level of precision, half precision, for example, right? Then you could do definitely more than 2x, maybe 5x, maybe even 10x. I don't know. This is a research question that is hard to answer. We really need more research in understanding where we can use these different levels of precision in a given application.
Okay, so there's one question that I think is more a comment, but you can go for the final question, I think. In trying to optimize mixed precision code, does each variable contribute to the error and the speed up independently?
Independently. I don't know what this means. What is independently here? I don't understand what is meant by independently here. I guess the question is, what are the dependencies of a given variable in terms of influencing the speedup?
Okay, so the participant's writing a little more here. So let's. Okay, so while we wait for the participants to finish the question, I'd like to take the opportunity to announce what is going to happen here, to say what is going to happen with the series at the end of the year, the rest of the year. We're skipping November because of the SC conference. We have people are very busy, and at December 11, we are working on a webinar for that date, and the topic and the speaker still to be announced. Remember, to all participants, please, we'd like to improve the series. Give us feedback on the recording and the slides and the question and answers. All we have two links. All the material related to this webinar will be available there. So going then back to the question, Ignacio. All right, so in trying to optimize mixed precision code, does each variable contribute to the error and speed up independently? It's like if you change the precision of variable 1, you'd some error and the speed up and changing the precision of variable 2, you'd some error and the speed up. So does the total error and the speed up add together?
So yeah, I don't know how to answer this. So one thing I have to say is that changing the precision of variables, I don't think is the right approach, because a given variable will affect several operations, or could affect several operations, actual instructions in your program. So if you change the precision of one variable, this may affect 10 or maybe 20 instructions in your program, right? And what you really want to change is the operations and the data, right? So maybe the best program that I want out of those 10 operations, maybe I want to change 3 operations only out of 10. But if I change the type of the variable, I will either change all the operations or none of them. Right? So really, this approach of changing variables is probably not the best, in my opinion. I don't know if this answers the question, but I guess I would need to understand better how do we calculate the error here and what kind of error we want to optimize here.
Yeah, so for the sake of time, I think we can stop here so that the participant, if he or she would like to add more to the question, I think we can address the question later. So I'd like to thank everybody for joining us today for this webinar, and also, of course, Ignacio, thank you very much. A number of very good, very nice, interesting questions here. Thank you all, and